Hello students. In the last lecture, we studied about our chapter number 1 from part 1, complex number. In this lecture, we see what is the imaginary unit, the definition of complex number. A number which is of the form a plus bi is called as a complex number, where a and b both are real numbers and value of I is equal to square root of minus 1. Also, we see the topic algebra of complex number. In that, we study about equality of two complex number, conjugate of a complex number, then properties of conjugate of complex number, addition of complex number, their properties, scalar multiplication, subtraction of complex number, multiplication of complex number, powers of complex number means powers of I, division of complex number and their properties. This we studied in the last lecture. Now, in this lecture, we solve some examples from that topic. So, we solve some examples from our exercise number 1.1. So, see the first example. The common instruction for first example is simplify the following. So, see the first example is square root of minus 16 plus 3 into square root minus 21 plus square root minus 36 minus square root of minus 625. So, see the solution. Consider the given term square root of minus 16 plus 3 into square root minus 25 plus square root minus 36 minus square root of minus 625. Now we know square root of minus 1 is equal to I. So we rewrite all these square roots in this way. Here square root of 16 into minus 1 plus 3 into square root of 25 into minus 1 plus square root of 36 into minus 1 plus square root of 625 into square root minus 1. Now in each the term, the value of square root of minus 1 is equal to I. Also, square root of 16 is equal to 4. We know that value. Square root of 25 is equal to 5. Square root of 36 is equal to 6. Similarly, square root of 625 is equal to 25. So substituting all these values, here we get value for this first root is 4i. Here square root of 25 into minus 1, it is 5i. Square root of 36 into minus 1, it is 6i. And square root of 625 into minus 1 is 25i. Now, using these values, we get it is equal to 4i plus 3 into 5i plus 6i minus 25i. Now here 4i plus 6i it is 10i. 10i minus 25i it is minus 15i. So minus 15i plus 3 into 5i it is plus 15i. So minus 15i plus 15i it is equal to 0i means 0. And so we get the simplification for this first example is 0. Now see the second example. It is 4 into square root of minus 4 plus 5 into square root of minus 9 minus 3 into square root of minus 16. Now simplify again this example in the similar way as that of example number 1. So solution, consider 4 root minus 4 plus 5 into root minus 9 minus 3 into root minus 16. Rewrite all these terms, we get 4 into square root of 4 into minus 1 plus 5 into square root of 9 into minus 1 minus 3 into square root of 16 into minus 1. Now use the same criteria. Square root of minus 1 is I in each term and square root 4 is 2, square root 9 is 3, square root 16 is 4. So we get it is equal to 4 into 2i plus 5 into 3i minus 3 into 4i. Open all these brackets. Here we get it is equal to 8i plus 59 minus 12i, and it is equal to 11i. And so it is a simplification for this example number 2 in the example number 1. Now see the second example. So the common instruction for this second example is write the conjugate of following complex numbers. We have to given some complex number, and our aim to write here some conjugate of the given examples, means given complex numbers. So see, the first complex number is 3 plus I. Now we know if Z is equal to A plus BI is a complex number, then its conjugate is Z bar, it is equal to A minus BI. Means the conjugate of a complex number is obtained by replacing only the sign of imaginary part. फक्त इमॅजिनरी पार्टचं चिन्ह बदललं म्हणजे आपल्याला त्याचा कॉम्प्लेक्स कॉन्जुगेट हा मिळतो. अँड सो हियर फॉर दिस एक्झाम्पल or for the given complex number 3 plus I, the conjugate of complex number 3 plus I is 3 minus I. We change here only the sign for the imaginary part. Okay, so see the second example. It is minus square root minus 5. So first we write this number in the complex number form. So solution, we have minus of square root minus 5, it is equal to minus square root 5i. Now this is a pure complex number because here the real part is 0. And here if we change the sign of the imaginary part, it becomes square root 5i, and it is nothing but the conjugate of this complex number, and therefore the conjugate of complex number minus 5 square root 5i is equal to square root 5i. Third, minus root 5 minus root 7i, and therefore in the solution conjugate of complex number minus 5 minus square root 7i is equal to minus 5 plus root 7i. Remember, we change only the sign of imaginary part. The sign of real part is as it is, because here since the imaginary part is negative, so in the conjugate the imaginary part is positive and real part has the same sign. Okay, now see the next example. It is cos theta plus I sin theta. So in the solution conjugate of complex number cos theta plus I sin theta is cos theta plus, sorry, here make the correction, cos theta minus I sin theta. Make here the correction. Here instead of this plus sign we must write here the negative sign. Means the conjugate is cos theta minus I sin theta. Here is a printing mistake, so make the correction. Here write this positive sign as a negative sign. Means the conjugate of complex number cos theta plus I sin theta is cos theta minus I sin theta. Remember this correction. Okay. Now see the next example, example number 3. The common instruction is find A and B if. So the first example in that, A minus B plus A plus BI is equal to A plus 5i. Okay, so solution, given A minus B plus A plus B into I is equal to A plus 5i. Now we observe here in the LHS there is a complex number, also in RHS there is a complex number, and both the complex numbers are equal. Now we know the two complex numbers are equal if and only if their real parts are equal and their imaginary parts are equal. That means if two complex numbers are equal, then their real parts and imaginary parts are equal. Okay. So using the equality of complex number, here we get A minus B is equal to A. A minus B is equal to A. Since here A get cancelled, we remains with minus B is equal to 0, that is B is equal to 0. Also using equality, what we get, A plus B is equal to 5. If we compare their imaginary parts, we get A plus B is equal to 5. Now put here value of B as 0, we get A plus 0 is equal to 5, means A is equal to 5. Therefore we get A is equal to 5. and hence now we get the values of A and B. Hence A is equal to 5 and B is equal to 0. See the second example. Under this instruction means again we have to find here values of A and B. See the example. A plus B multiplied by 2 plus I is equal to B plus 1 plus 10 plus 2I into I. Solution. Given A plus B into 2 plus I is equal to B plus 1 plus 10 plus 2I into I. Now first here in the LHS we open the bracket. Means we write his LHS as a complex number. So here we get 2 into A plus B plus A plus B into I is equal to, here real part in RHS it is B plus 1. So and imaginary part is 10 plus 2I. So B plus 1 plus 10 plus 2A into I. Now again here use equality of complex numbers. So using the equality of complex numbers we get their real parts are equal and their imaginary parts are equal. So comparing first the real parts, we get 2 times A plus B is equal to B plus 1. That is 2A plus 2B is equal to B plus 1. If we take this B in LHS, it becomes negative. So now we remains with 2A plus B is equal to 1. We call this as relation number 1. Similarly, now compare the imaginary part. So also we get A plus B is equal to 10 plus 2A. So we get now A minus B is equal to minus 10. Call this as relation number 2. Now solve these two equations for values of A and B. So simply adding both the equations, we observe B get eliminate and we get value of A. So adding equation 1 and 2, we get 2A plus A, it is 3A. Here B get cancelled and 1 minus 10 is equal to minus 9. So we get 3A is equal to minus 9 and therefore A is equal to minus 3. Now if we put this value of A in the relation number either in 1 or in equation number 2. Put in one of the equation, we get value of B. So from equation number 1, if we put in equation 1, A is equal to minus 3, we get here minus 6 plus B is equal to 1, that is B is equal to 7. And hence we get A is equal to minus 3, B is equal to 7. These are the values of A and B for this example. Now see the second example. For this example again we have to find values of A and B. ABI is equal to 3A minus B plus 12I. So given ABI is equal to 3A minus B is equal to plus 12I. Again here both the complex numbers are equal, so using the equality of complex number. In LHS the real part is 0, so comparing the real part we get 3A minus B is equal to 0, that is B is equal to 3A. We call this as relation number 1. Also comparing their imaginary parts, we get AB is equal to 12. Now put value of B as 3A. So we get A into 3A is equal to 12. Dividing by 3, we get A square is equal to 4. Since A square is equal to 4, that means A has two values. Either A is 2 or A is minus 2. And therefore A is equal to plus or minus 2. If we put this value of A in equation number 1, again we get there are two values of B. So from equation number 1, B is equal to plus or minus 3 into 2, or 3 into plus or minus 2 means it is plus or minus 6. And hence A is equal to plus or minus 2 and B is equal to plus or minus 6. Now see the fourth example. For that again we have to find values of A and B, and that example is 1 upon A plus BI is equal to 3 minus 2I. Okay. Solution. Given 1 upon A plus BI is equal to 3 minus 2I. Now taking the reciprocal on both the sides, we get A plus BI is equal to 1 upon 3 minus 2I. Now we know one property of division. The division we see one property, and that property as 1 upon A plus BI is equal to A minus BI divided by A square plus B square. That means when we take the reciprocal here 1 upon a plus bi. It is equal to the complex conjugate of the complex number a plus bi, means conjugate of a plus bi is a minus bi, divided by square of real part plus square of imaginary part. So using this property, value of this 1 upon 3 minus 2i is 3 plus 2i upon 3 square plus 2 square. So use this property, and using this property we get now a plus bi is equal to 3 plus 2i divided by 3 square plus 2 square. Now 3 square is 9, 2 square is 4, so 9 plus 4 is 13, and therefore we get a plus bi is equal to 3 plus 2i upon 13. If we separate here the real and imaginary part, we get a plus bi is equal to 3 upon 13 plus 2 upon 13i. Now since both the complex numbers are equal, so again using the equality of complex number, compare their imaginary and real part, we get value of a is 3 upon 13 and value of b is 2 upon 13. Now see our next example, main example number 4. See the common instruction for this example number 4. Express the following in the form of a plus bi, where a comma b belongs to real number, I is equal to -1. State the value of a and b. म्हणजे आपल्याला खाली काही दिलेलं असेल एक्सप्रेशन, त्यांना आपल्याला a plus bi मध्ये एक्सप्रेस करायचं आहे आणि त्याच्यावरून आपल्याला a आणि b च्या व्हॅल्यूज फाइंड करायच्या आहे. सो सी द फर्स्ट एक्झाम्पल. इट इज 1 plus I into 1 minus I bracket raised to -1. Now bracket raised to -1 means it is 1 upon that term. Okay. So here solution, consider 1 plus I into 1 minus I bracket raised to -1. It is equal to 1 plus I upon 1 minus I. Now again 1 upon 1 minus I is 1 plus I upon 1 square plus 1 square. It is 1 plus 1. So we get 1 plus I multiplied by value of this 1 upon 1 minus I is 1 plus I divided by 1 plus 1. So it is equal to 1 plus I bracket square divided by 2. Now open this square. It is equal to 1 square plus 2 into 1 into I plus I square divided by 2. Now since I is equal to square root -1, therefore I square is -1. So using that I square is -1, we get here it is equal to 1 plus 2i minus 1 divided by 2. Now 1 minus 1 is 0. So 0 plus 2i upon 2, and it is equal to 0 plus I. Means now here we observe that it is of the form a plus bi. So which is of the form a plus bi. If we compare here, a is equal to 0 and b is equal to 1, and where a is equal to 0 and b is equal to 1. In this way we get here values of a and b. Now see the second example. Now second example is 2 plus I divided by 3 minus I into 1 plus 2i. Solution, consider the given term 2 plus I divided by 3 minus I into 3 plus I. First of all, open this bracket in denominator. So 2 plus I divided by 3 into 1 plus 2i minus I into 1 plus 2i. So it is equal to 2 plus I divided by 3 plus 6i minus I minus 2i square. Now using I square is equal to -1. Now we get here 2 plus I divided by, here minus minus becomes plus 2. So 3 plus 2 is 5 and 6i minus I, it is 5i. We use this result, I square is equal to -1. Now again 1 upon a plus bi is equal to a minus bi upon a square plus b square. Value of this 1 upon 5 plus 5i, it is 5 minus 5i divided by 5 square plus 5 square. So it is equal to 2 plus I multiplied by 5 minus 5i divided by 5 square plus 5 square. Okay, again we use here property for division of complex number. Okay, and so now it is equal to 2 multiplied by 5 minus 5i plus I multiplied by 5 minus 5i divided by 25 plus 25 is 50. Now open this bracket. It is equal to 10 minus 10i plus 5i minus 5i square. But I square is -1, minus minus becomes plus 5, whole divided by 50. Now 10 plus 5 is 15 and minus 10 plus 5 is -5. So 15 minus 5i divided by 50, and therefore the given expression, that is 2 plus I divided by 3 minus I multiplied by 1 plus 2I is equal to 15 minus 5I divided by 50. If we separate here the terms, it is equal to 15 upon 50 minus 5 upon 50I. Dividing by 5, we get here it is 3 upon 10 minus 1 upon 10I, which is of the form a plus bi, where a is equal to 3 upon 10 and b is equal to minus 1 upon 10. In this way, here we get the values of a and b. Now see this third example under this instruction. It is 3 plus 2i divided by 2 minus 5i plus 3 minus 2i divided by 2 plus 5i. Solution: consider the given expression 3 plus 2i upon 2 minus 5i plus 3 minus 2i upon 2 plus 5i. Now take here the LCM. LCM is product of both the denominators. It is 2 minus 5i into 2 plus 5i. So in the numerator now we get 3 plus 2i into 2 plus 5i plus 3 minus 2i into 2 minus 5i. Open the brackets in numerator. We get 3 into this bracket means 6 minus 59 plus 4i plus 10i square plus 6 minus 59 minus 4i minus plus 10i square. And in the denominator it is 2 square plus 5 square means 2 square plus 5i bracket square minus 5i bracket square means it is 4 minus 25i square. Now in all the terms, value of I square is minus 1. So substituting that value, here we get 6 plus 59 plus 4i minus 10 plus 6 minus 59 minus 4i minus 10 divided by 4 plus 25. Now 59 minus 59 get cancelled, 4i minus 4i get cancelled. Now 6 plus 6 is 12, minus 10 minus 10 minus 20. So 12 minus 20, it is minus 8. So it is equal to minus 8 upon 29. We rewrite this term as minus 8 upon 29 plus 0i, because our aim to reduce the given expression in the form of a plus bi. So now which is of the form a plus bi, where if we compare, we get a is equal to minus 8 upon 29 and b is equal to 0. In this way, in this example, we get the expression in the form of a plus bi and again the values of a and b. Now see the example number 4. It is 4i raised to 8 minus 3i raised to 9 plus 3 divided by 3i raised to 11 minus 4i raised to 10 minus 2. Solution: consider 4i raised to 8. We consider here this expression first. Okay. Now to simplify this, our aim to use here the result powers of I. In the powers of I, we see we generalize the result as I raised to 4n is equal to 1. I raised to 4n plus 1 is equal to I raised to 4n plus 2 is equal to minus 1. I raised to 4n plus 3 is equal to minus I. Okay. I raised to 4n is equal to 1. I raised to 4n plus 1 is I. I raised to 4n plus 2 is minus 1. I raised to 4n plus 3 is equal to minus I. We use this result to simplify this expression. So consider the expression and rewrite it as. So we rewrite it as 4 into I raised to 4 into 2 minus 3 into I raised to 4 into 2 plus 1. 9 can be written as 4 into 2 plus 1 plus 3. Now this I raised to 11 can be written as 3 into I raised to 4 into 2 plus 3 minus 4 into I raised to 4 into 2 plus 2 minus 2. Now we know I raised to 4n, it is 1. So value of this I raised to 4 into 2 is 1. Here is I. Here is I raised to 4n plus 3. It is minus I. And I raised to 4n plus 2. It is here minus I. Minus 1. So put all these values here, you get 4 into 1 plus 3 into I, 3 into minus 1 minus 4 into minus 1. So using these values, we get the expression as 4 into 1 minus 3 into I plus 3 whole divided by 3 into minus I minus 4 into minus 1 minus 2. So it is equal to 4 into 4 plus 3, it is 7 minus 3I. Here we get minus minus plus 4 plus 2, sorry, plus 4 minus 2, it is 2, and this is minus 3I. Now, again using the property of division, value of 1 upon 2 minus 3I, it is 2 plus 3I upon 2 square plus 3 square. So it is equal to 7 minus 3I into 2 plus 3I divided by 2 square plus 3 square. Now, in the numerator, product of these two bracket is there, and 2 square plus 3 square, it is 4 plus 9, 13. So it is equal to 7 into 2 plus 3I minus 3I into 2 plus 3I divided by 13. Now open the brackets in numerator. It is equal to 14 plus 21I minus 6I plus 9, because here minus 3I into 3I, it is minus 9I square. But value of I square is minus 1, so minus minus becomes plus 9. Now 14 plus 9, it is 23, and 21 minus 6, it is 15. So here we get 23 plus 15I divided by 13. And therefore, the value for the given expression means 4I raised to 8 minus 3I raised to 9 plus 3 divided by 3I raised to 11 minus 4I raised to 10 minus 2 is equal to 23 plus 15I upon 13. If we separate the terms, we get it is equal to 23 upon 13 plus 15 upon 13I. Now which is of the form A plus BI, because our aim to reduce the given expression in terms of A plus BI, and we have to find the values of A and B. So which is of the form A plus BI, where A is equal to 23 upon 13 and B is equal to 15 upon 13. This is about the fourth example in our example number 4. Now see the main example number 5. Show that minus 1 plus root 3I bracket raised to 3 is a real number. Means cube of given complex number is a real number. This is we have to prove here. So solution, consider the given cube 1 plus root 3I bracket cube. Now we use here the formula to find the cube of A plus B. Means A plus B bracket cube is equal to A cube plus 3A square B plus 3AB square plus B cube. We use this formula. Here if we compare, value of A is minus 1 and value of B is root 3I. So using this formula means value of A plus B bracket cube is A cube plus 3A square B plus 3AB square plus B cube. Using this formula, here we get the value of minus 1 plus root 3I bracket cube is equal to minus 1 cube plus 3 into minus 1 square multiplied by root 3I plus 3AB square means plus 3 into minus 1 into root 3I bracket square plus B cube means root 3I bracket cube. Okay. Now we know value of I square is minus 1 and I cube is minus I. So here we get now minus 1, because minus 1 cube is minus 1. Here minus 1 square is 1, means this term is positive. We get here 3 root 3I. Here now root 3I bracket square, it is 3I square. Because of this minus sign, it is negative. So minus 9I square plus root 3 cube, it is 3 root 3 into I cube. So 3 root 3 I cube. I square is minus 1, I cube is minus I. So minus minus becomes plus 9 here, and we get here minus 3 root 3I. So it is equal to minus 1 plus 3 root 3I plus 9 minus 3 root 3I. Because we use this result, remember here I square is equal to minus 1 and I cube is equal to minus I. We use these two results here. So I write here that result. So here minus 1 plus 9 is 8 and this term get cancelled. And we observe this, there is no complex number. We know every real number can be written in the form of complex number by writing its imaginary part as 0. But it is purely real number. and which is a real number, and hence -1 plus root 3i bracket cube is a real number. So these are some examples from the topic, means from our exercise number 1.1. We solve some more examples in our next lecture. So see you again in the next lecture.